Hello everybody, this is going to be our last lecture for intermolecular forces. We are going to look at something called vapor pressure, and then we're also going to look briefly at how phase changes can happen, since those are related to how the molecules are interacting with each other. Vapor pressure is the pressure of the vapor once the reaction or the container is at equilibrium. This pressure above the container is determined mostly by the size of the IMFs inside the liquid. As your temperature increases, that vapor pressure will increase. More of those molecules will be able to be in the gas phase, leaving that container as your temperature goes up. If something has a very high vapor pressure, we say that it is volatile. Have you heard of that phrase, volatile? A high vapor pressure means that a lot of those particles can be in that gas phase. When you think about boiling point, you think about seeing at what temperature do you start to see those bubbles form, right, in your pot of water as it boils. But that's not exactly the right way to think about it. Boiling point is the temperature at which the vapor pressure will equal the pressure from the atmosphere. At that point, those particles can be leaving that liquid and turning into the gas. We will often see big bubbles, big pockets of air, right, when we're boiling our water on our stove. But that's not really what we mean. The big bubbles that you see, that is just a visual, that is an observation of something that can happen once you reach this point. So see our container here, and we have the liquid down here at the bottom, and up here you can see the vapor. And these little particles are bouncing all over the place because they're a gas, right? Now sometimes particles will leave the liquid and go into the gas phase, but sometimes they'll go the opposite direction. It's an equilibrium, isn't it? Particles are leaving the liquid phase at the same rate they are going back into the liquid phase. They're going from liquid to gas back and forth at the same rate, so it doesn't appear as though anything is happening when we just look at our container. You might remember in Honors Chem, you did a lab where you were collecting a gas and you had to subtract out the amount of water vapor that was inside your gas that you were trying to collect. This idea of vapor pressure explains why, when you were collecting your gas over water, some of the particles were water molecules, not just the gas you were trying to collect. I love this picture. This comparison here. Down here we have very high IMFs. These particles in the liquid phase are very attracted to each other. They do not really want to be in the gas phase. There's not a lot of pressure up here because there are not a lot of particles. Here in the middle we have kind of some medium level IMFs and some medium level pressure up above. And here, in red, we have very low IMFs. These particles do not care about each other. There's not much holding them near each other in that liquid phase, which means a lot of them are available to be up here in the gas phase. And if there's a lot of particles up here, they're going to be hitting that container a lot, which means they will have a high pressure. They're inverses of each other, aren't they? If they are asking about why does something have a high vapor pressure, it's because there's low IMFs. If they ask why something has a high, or if something has low vapor pressure, it's because they have high IMFs. If there's not much keeping them together near each other in a liquid phase, they're not going to stay that way, right? They're going to be going into that gas phase. This one here in red, we would say is more volatile. Now, if you increase the size of your container, the pressure will go down, won't it? So if you don't have a lot of gas particles, you're not going to have them condensing back to the liquid very quickly. So for a little bit, once you've made that change to the volume, for a little bit of time, you'll have more things vaporizing than condensing. And therefore the amount of your vapor will increase and you'll establish that equilibrium again, right? Sometimes they like to connect this IMF stuff, this vapor pressure stuff, into equilibrium questions. Remember when I told you equilibrium was never going away? This is another example of it. It's not going away. Remember, everything wants to get to that equilibrium point. Now, a little bit related, a little bit different are these phase changes, okay? In order for something to go through phase changes, we have to think about the energy that's involved. So this is connecting IMFs and equilibrium and thermo, isn't it? It's all kind of coming together. You should remember this from your honors chem. We are not going to go into heating curves very much. If you need a refresher on heating curves, go watch the honors chem video. I'm not going to record the same thing just for AP Chem. You should hopefully remember this from honors. Remember that in our sloped areas, we are increasing our temperature. And on the flat areas, we are increasing the distance between our particles. I would always tell my class you have to speed things up, and then you got to spread out before you can speed up even further. Kind of like when you're driving a car. If you're bumper to bumper, you shouldn't be going 70 miles an hour, right? You need to wait for there to be some space between molecules before they can keep increasing their speed. Remember, a cooling curve is just going the opposite direction. Energy is absorbed going up and is released going down. In AP Chem, they don't often ask you to do big, giant heating curve calculations where you're going all the way from an ice to a steam. They'll often just ask for 1 or 2 lines, which is nice, but make sure you can do a huge one, right? Make sure you understand how we did these in honors chem. It's very important that you understand that the temperature is constant when you're on these flat spots. And those are the phase change points. This is melting. This is vaporizing. If you go backwards, this is condensing, and this is freezing. People often don't really believe that the temperature is the same. They say, but my water is getting hotter, right, while it's boiling. No, it's not. It's staying at 100 degrees. Now, if your water's not being stirred very well, you may have hot spots and cold spots, but that's due to an issue with not having good stirring, right? Same with ice water. When you have ice mixed with water, and the ice is melting into that water, it stays at 0 degrees until every bit of ice is melted. But if it's not stirred very well, you could get hot spots and cold spots. But if we have a nice perfect system, like we're always assuming, right, then you would end up with a nice plateau for your phase change temps. Phase diagrams are a little bit different. They are trying to show you all the phases that can be present at various combinations of temperatures and pressures. You may see some special things on a phase diagram. There's a spot called a critical temperature. That's the point at which the temp is so hot, it's so high that you can't get it into a liquid anymore. Even if you increase that pressure and try to cram those molecules together, you can't do it. It's going to stay a gas. Critical pressure is the pressure it would take to liquefy at that point. I like to just throw these in there because sometimes you'll hear these in older videos or older problems and just want to make sure you know what they are. So here is what a phase diagram might look like. Okay. You can see temperature increases here going to the right, pressure increases going up. If you have something at a very cold temperature and a decently high pressure, right, makes sense it would be a solid. If you have a decently high pressure, but it's a little bit warmer, it would be a liquid. And if you keep heating it up, it would turn into a gas. The boundaries between these colored regions here are where the phase changes happen. If you have very low pressure and low temperature, you can get something to go from a solid straight to a gas or vice versa. Sublimation, deposition. Solid to liquid, melting and freezing. Vaporization and condensation. Here's another one, the triple point. This is the temperature and pressure combination in which you can have all three phases present at the exact same time. Kind of a crazy idea, but there is this special point at which you can have a solid, a liquid, and a gas all at the same time. Here's an example of water's phase diagram. The slope of these lines can be interesting. Having this negative slope here between a solid and a liquid is not very common. That's something that's pretty special to water. And that has to do with the fact that liquid water is more dense than the solid. Water molecules kind of spread themselves out when they make their crystal structure, and that's not a typical thing. Usually you would see a positive slope here because usually the solid's more dense, right? Sometimes these get really crazy because you may have different types of solids. For example, remember how we have diamond and graphite for carbon? And to get diamond, what do you need? You need really high pressures. So you can see that the diamond is up here at the top. Sulfur is one that has different types of structures for their solids. Long time ago, you used to have to learn what all those crazy names mean and what those different arrangements were. We don't have to do that anymore, thankfully. So when you see these weird names, that's just telling you different types of solids. Now, we used to teach a lot of crystal structure stuff, which goes in with the IMF chapter. We're not going to do that anymore. If you're interested, if it's something you think is neat, you could open up the PDF and keep going. But a lot of that stuff has been cut out now, and we're not going to cover it. Be careful on really old FRQs and old multiple choices because you may see crystal structures added in. You know, if you're pulling up an old AP exam to practice, just skip those crystal structure questions. All right, everybody, that is it. I hope this was helpful. Bye.